Welcome to lesson 4.7, solving linear equations using graphs. So we know there's two different ways to solve linear equations. One is algebraically and one is graphically. So prior to this lesson, you've mainly been solving linear equations in this chapter by using graphs and then checking the solutions algebraically, meaning you could plug in one of the coordinates or ordered pairs into the equation to make sure that it works. Now in this lesson, we're going to look at how to use the graphing aspect to check the algebraic solutions. So we'll be solving them and then checking it graphically, rather than checking it algebraically. So we have three steps for solving linear equations graphically. The first step is to write the equation in the form ax plus b equals 0. The second step then is from first step to write the related function y equals ax plus b, or if it's slope-intercept form, y equals mx plus b. They're just keeping the a based on this previous equation. And then in step 3 asks us to graph the equation y equals ax plus b, where a is the slope and b is the y-intercept. So this is slope-intercept form. The a is our slope, just carrying over from the first two steps. And then an important reminder is that the solution to this, ax plus b equals 0, is the x-intercept of this final graph. So whatever this solution is, that would be, so if we solve this for x, that would give us the x-intercept of this graph. So let's look at these three steps and apply them. Example 1 asks us to solve this algebraically and then check the solution graphically. So we're going to follow our three steps here as well. So the first thing we want to do, no matter what, is we're putting it in this ax plus b equals 0 form. So if our original equation is 2x minus 5 equals 1, the 2x is already the ax. The plus b, well, we have the minus 5, but it doesn't equal 0, it equals 1. So we need to rewrite this so it equals 0. So I need to take the 2x minus 5 equals 1, subtract 1 from each side, and I have 2x minus 6 equals 0. That is now in the form ax plus b equals 0. If I were to solve this algebraically, so I just did my first step for checking it graphically. Solving it algebraically is as simple as this. 2x minus 5 equals 1. So I could add the 5 to each side, and 2x equals 6, so x equals 3. Or if I took the 2x minus 6 equals 0, add the 6 to each side, 2x equals 6, divide both sides by 2, and x equals 3. So this is how we would solve that algebraically. So our solution algebraically tells us x equals 3, meaning our graph should also include the point x equals 3 or cross the x-intercept at 3. So we're going to check to see if that graph crosses the x-intercept at 3 like our algebraic solution says. So the second step, writing the related function y equals ax plus b. You just take your answer from the first step, ax plus b equals 0, and you replace the 0 with the letter y. So if 0 equals 2x minus 6, our related function would be y equals 2x minus 6. And then we're going to graph that, where we know what's attached to the x is the slope, and what's the plus or minus on its own is the y-intercept. So my y-intercept is a negative 6, so I'm going to start my graph at 0, negative 6, and then I'm going to follow the slope which is 2. So 2 over 1 tells me from the y-intercept, go up 2, right 1. So from 0, -6, my line would go up 2, right 1. There's the next point. Up 2, right 1, up 2, right 1. So then if I look at the graph crosses the x-axis at 3. So x equals 3 for the x-intercept. X equals 3 when we checked it algebraically. So the graph confirms our algebraic answer that x equals 3. Now, in example 2, they want us to graph it and then to check the solution algebraically. So the first thing we want to do is these 3 steps for graphing. So we're going to take the original equation and write it in ax plus b equals 0. So if I have 4/3 x plus 3 equals 2x, I need to get this 2x to be 0. So I'm going to subtract 2x from each side. So 4/3 x minus 2x, subtracting from a fraction. So I'm going to make a common denominator. So 2x is 2 over 1, which is the same as 6 over 3. So with my common denominators, I'd have 4/3 x minus 6/3 x. That gives me a negative 2/3 x. So that's where this part came from. The 4/3 x minus 2x is a negative 2/3 x. So writing it in ax plus b equals 0, it'd be a negative 2/3 x plus 3 equals 0. So second then, we want to write that in the related function y equals ax plus b. So we replace the 0 with a y. So y equals negative 2/3 x plus 3. Now the third thing we're going to do is graph negative 2/3 x plus 3. Well, it's in slope-intercept form. So the positive 3 is my y-intercept. So over 0 up 3 gives me my first point. My slope is a negative 2/3. So I'm going to go from 0, 3 down to right 3, and there's my next point. Down 2, right 3, there's my next point. Connect your points and draw your line. Now, what we want to do is we want to substitute the x-intercept, so where it crosses the x-axis, into the equation. And we're going to check algebraically then if that works. So if we would cross the x-axis at 3, like in the previous problem, we're going to put a 3 in for x into the original equation to see if that's true. Well, now we're crossing the x-axis at 4.5 or 9/2. So the x-intercept appears to be 9/2 or 4.5. So we're going to plug 9/2 into this original equation for both x's. So wherever there is an x, we're substituting in the 9/2. So this equation becomes negative 2/3 times 9/2 plus 3 equals 2 times 9/2. And what we want to see is if the left equals the right. When we put in the 9/2 for x, if this solution's true, then our graph is accurate. So this becomes 6 plus 3, and the right-hand side is 9. So does 6 plus 3 equal 9? Well, 9 equals 9, so yes. So 9/2 for our x-intercept is correct. We graphed the equation, and we checked it algebraically. So 2 ways for each of these that you can do these. You can solve it algebraically and then go through the 3 steps to draw the graph and check it. Or you could draw the graph and then wherever it crosses the x-axis, put that back into the original equation to see if it's true. And then we are going into the word problem. And in your practice problems, most will be like the first two examples. I just want to go through one example of the word problem so you can see two different approaches. So in this word scenario, it says, based on the data from 1980 to 97, a model for the number n in millions, which is the number of registered nurses in the USA, is n equals 0.055t plus 1.26. T is the number of years since 1980. According to this model, in what year will the US have 2.5 million registered nurses? So we need to take this 2.5 and put it in for n. So our equation would be 2.5 equals 0.055t plus 1.26. So the first approach is we can solve this using algebra and then graph that line to see where it crosses the x-axis to get our answer for how many years. So in this first approach, we want to use the algebraic approach and the graphing. So to solve this for t, I'm going to do that right here. We want to solve for whatever t may be. So we're going to first get rid of, oh, sorry, I lied. I'm solving for t down below. First, I need to rewrite this in ax plus b equals 0. So my apologies. In order to solve for t, we first need to write it into the ax plus b equals 0. So I want to get 0 where 2.5 is. So I'm going to subtract 2.5 from each side, and 0 equals 0.055t minus 1.24. Now we can use that to find t. So I'm going to find the t-intercept, or find out what t is. Same thing we would do for x, we just have t this time. So 0 equals 0.055t minus 1.24. Add the 1.24, so 1.24 equals 0.055 times t. Divide by the 0.055, and we get t equal to approximately 22.5. So that tells me I should be crossing the t-axis in this case, or x-axis, at 22.5. Then we can check that with our graph. And with our graph, slope-intercept form, my y-intercept is at a negative 1.24, and our slope is right here. So if this was a fraction, it would be 55 over 1,000. So we would technically go up 55 and write 1,000. So the graph of that gets real tricky. So if I just graph that, I know I'm going to use a shortcut. I'm just going to use my x and y intercept. I knew my x-intercept from solving for t was at 22.5 and 0. So there's my point, 22.5 and 0. The y-intercept, 0, negative 1.24. So over 0 down 1.24, connect them to draw the graph. So either way, that tells me t should be about 22.5 years later. The other approach you can use to use the graphing is to solve for both sides by graphing both sides. So if we have 2.5 equals 0.55t, or 0.055t plus 1.26. To graph the left-hand side, you just set it equal to y. So y would equal 2.5, meaning a horizontal line at 2.5. Then to graph the right-hand side, y equals, and here's our equation. So the y-intercept would be up 1.26, and here would be our slope. Now again, these aren't nice numbers, but if we did our best to graph it, we would get this blue line here. Now where the two lines intersect, from that point where those two lines intersect, you go straight down to the x-intercept, and wherever that number approximately is, tells you how many years till they meet. So one case would be to graph both sides of the equation, and where they cross, that X value gives you the number of years. The other option is to just graph that single line by finding the two intercepts and connect them. And either way, we get 22.5 for the X value, or T value in this case, where they meet, or where the single line crosses that intercept. So both of those approaches tell me T is about 22.5. So if T is the number of years since 1980, that tells me that our numbered registered nurses will equal the 2.5 million in approximately the year 2002, sometime in the middle of that year, if it's taking roughly 22 and a half years since 1980. So this lesson shows you how to use graphing to support your algebraic answers. Now, realistically, as you're solving these, you're going to either do algebraic or graphic, and then you're going to move on. This lesson is just reassuring and showing you how to use the two different approaches, algebraic and graphically, to make sure your answers are correct.